I think I've done for pre-calc in lessons 3.1 through 3.4, which involves logarithms and exponential expressions and equations. So far, what we've done in class is I gave you that big old packet that you guys were supposed to work on that had a whole bunch of different terms and different things that you needed to either research or evaluate or figure out. Instead of just going over all those different problems, I'm going to just talk about the different things that you needed to know in order to do them. So this is just going to be one big lecture. I apologize for the longness of it, or the length of it, I should say. And here we go. So 3.1 is all about exponential equations. And so an exponential equation, a generic one, is f of x, where instead of normal exponents like x or 3 squared, the value that changes, the x, is now my exponent. So a stays the same the whole time. It doesn't change. The only thing that changes is your x. And this x is your power or your exponent. The a is your base. And then f of x is the answer you get out. Now, we've already talked about e, which is the natural exponent. That's f of x equal to e to the x. And e is what we call the natural base. And the reason it's a natural base is it's kind of like pi in that it's a number that occurs in nature. We had to discover what it was, but it was already there. We didn't come up with it, we found it. And it's kind of like a natural number, but it's a natural irrational number. Kind of like pi. Pi goes on forever, right? We approximate it with 3.14, but it goes on for quite a while. 3.1415926 and so on. E is very similar to that. It represents a single number that goes on forever as a irrational number. So using these exponents, we can apply it to different situations. For example, we talked about when I compound interest n amount of times per year. So we have n compoundings per year. And that formula we found out, and we talked about it, was the total amount after the amount of time is the original principal times 1 plus whatever rate you are compounding it by, divided by how many times you do that, raised to the number of times you do that for the amount of time. In years, usually, is how they do it. We can also compound interest continuously. And this one's a little different, or we'll just say continuous compoundings. It's a little different in the fact that instead of the 1 plus r over n, we have a equals our original principal times e raised to the rt. And you're probably asking yourself, where does e and r come from? Well, where did the nt go, and where did 1 plus r over n go? Well, what we did is we let m be n over r. And what we were able to do is in the original equation, replace r over m with 1 over m. And then n in the exponent became rm. And so what happens is, as we look at 1 plus 1 over m raised to the rm, and then raise that to the t, or excuse me, this should be just m inside, and on the outside should be RT. So as I look at this value in here, as m gets bigger and bigger and bigger, it gets closer and closer to the value of e. And so that's how we get this equation. So as m gets impossibly large for us to count, the number 1 plus 1 over m raised to the m power approaches e. And so that's what we did in the first section. And really this first section where we're talking about exponents, we're just introducing what an exponential equation is. We're not really doing much with it yet, except for using it in compound interest. Section 3.2, this is when we introduce the idea of a log. And so a log is if I have an equation y equals log base a of x, that's going to be the same as if I rewrote x equal to a raised to the y power. Now this only works if one is the same as the other, meaning it goes both ways. So if you have x equal to a to the y, so if you have an exponential equation on the right, I can rewrite that exponential equation as a log equation, and vice versa. So x equal to a to the y is the same as y equal the log of base a raised to the x power. A few stipulations: we have to have x greater than 0. If x is less than or equal to 0, what we're saying is a to the y power is equal to 0, and that's not possible. You can't raise any number to another power and get 0, or a negative number. We also have to have a greater than 0. I can't take 0 and raise it to a power. That's just going to give me 0. It doesn't really make sense for a to be equal to 0. If a was negative, that doesn't really make sense either, just because if I take a negative value for a, it's gonna, and I have like an odd exponent, that's gonna give me a negative value out. It doesn't work when we have these situations. And that negative number is just gonna be the same as if I just pull out the negative from the a anyway. The other thing is, a is not allowed to equal 1. I would think this is kind of obvious, and the reason for that is, every time you raise 1 to a certain power, it's always going to give you 1. So this isn't really going to help us if a is equal to 1. Another way to write y equal log base a of x is f of x equal to the log base a of x. And that's how I read it. I say log base a of x. Okay? Or f of x is equal to the log base a of x. So this section also brings the actual properties of logs. And so one of the properties of logs says that if I have log of a of 1, that's going to equal 0. And the reason for that is because a raised to the 0 power is equal to 1. Any number raised to the 0 power is equal to 1. Only makes sense that the log base a of 1 equals 0. What is the power of a that gives me 1? That's how you should read that. That's how you should think of that. The second property is log base a of a is equal to 1. And the reason for this is, what power of a gives me a? Well, that's 1. A to the first power is a. So anytime you see log base a of a, you can automatically turn that into a 1. Now this kind of works very similar, this next property. log base a of raised to the x power is x, and a raised to the log base a of x is also equal to x. These are inverses. So some of you were kind of wondering why it's equal to x instead of like 1 raised to the x. The reason for that, or you were probably wondering why it's not just x, or it's not x times the log of a for the second one. It's because they're inverses. So if you took one and substituted it in for the other, you're going to get x back out. It's just the way it works. If you remember when we talked about inverse functions, you substitute one into the other, you get out x. Same with you do the other way. That's what happens here. And then the last property that we're going to talk about here is if the log base a of x equals the log base a of y, then x equals y. This is what we call the one-to-one property. Okay? Pretty simple. Now, the next thing that we talked about in this section was the natural log. And the natural log is the counterpart to the natural exponent, or the natural base, e. So our stipulations here is x has to be greater than 0. And so when we have this, we say y is equal to the natural log of x. If and only if, that means it goes both ways, x equals e raised to the y power. And the way I write this as a function is f of x equals log base e of x, which is the same as the natural log of x. So anytime you see natural log of x, you should automatically think log base e. And so when I think of this situation, I can apply the properties of regular logs here in the properties of the natural logs. So they are actually almost one and the same. The only difference is we're using natural log and e as opposed to any log of any base. So if I have the natural log of 1, that's equal to 0, because if I raise e to the 0 power, that's 1. And remember, log base e of x is the same as the natural log of x. So if I say log base e of x is equal to 1, then I'm saying e to the first power equals x. So what does x have to equal? Well, that would have to equal e, for example. So if I say the natural log of 1 equals 0, that means e to the 0 equals 1. Or log base e of 1, that would have to equal 0. E to the what power gives you 1? Well, that's 0. I'm kind of saying the same thing over and over again, hoping you guys will understand it through the video. Anyway, natural log of e, that's going to be equal to 1, because remember, this is log base e, and then I have an e. When I have the same base as I do inside the log, that's going to equal 1, right? And the reason for this is e to the first power is e. Next, we have the inverse property, which is the natural log of e to the x. That's going to equal x. And e to the natural log of x will also equal x. These are my inverse properties. And then the last one is the if and only if statement, the one-to-one property statement. If the natural log of y, well, we can do x first. If x equals the natural log of y, then x has to equal y. And this is, again, what we call the one-to-one property. Section 3 is the properties of logs. A little bit more properties of logs, I should say. So um, this is where we bring in the change of base. Now, we didn't really talk about this much, um, but we did talk about it last class, those of you who were absent. So the change of base sounds exactly what it sounds like. I can change my base of my log. So basically, I'm allowed to convert bases. So that's why this property, this theorem, whatever you want to call it, comes in handy. Because if I don't have a base that is really easy to use, I can change it. So what this says is if I have a log base a of x, and that doesn't really work for me, let's say, I can say this is going to equal the log base b of x over the log base b of a. And it doesn't really matter what base I choose for b. Make it easy on yourself. If a is something that's easily reduced, choose a base for b that makes it reducible. Same with x. If x is what you want to reduce easily, you choose a base for b that makes it easily reducible. And this goes for any base b. Okay? Now we can apply this to log of base 10 as well. So if I have the log of a, base a of x, I can rewrite this as log base 10 of x divided by log base 10 of a. This is how it works in base 10. Same situation, the only difference is now I know my base is 10 as opposed to any base for b. This also works for the natural logs and for base e. So if I have log base a of x, I can rewrite this as the natural log of x over the natural log of a. So this is if my base is e. I use this a ton in my later college courses. I loved this base e transformation, change of base property theorem, whatever you want to call it. It was a really, really good helper for me. I remember a lot of proofs I had to do on this. Next, we had three other properties. We had the product, the quotient, and the power property. And these are pretty much exactly the same for any base a and for the base e. They just look a little different, or for the natural log, I should say. So I'm going to make a little table here. So we have what it looks like for base a, and then we have it for the natural log. You can also abbreviate it like that. So we have the product property. Basically, it sounds exactly what it sounds like. You're going to be multiplying things, but what you're multiplying is inside the log. So if we have log base a of uv, that's going to be the same as log base a of u plus log base a of v. Now it also applies to the natural log. If I have the natural log of uv, that's the same as the natural log of u plus the natural log of v. That's the product property of logs. We also have the quotient property, which you would guess it is division. So if I have the log base a of u divided by v, that's log base a of u. Oh wait, this time we're dividing, and last time we multiplied. Last time when I split it up, it was addition. So what do you think it's going to be this time? Yep, it's going to be subtraction. So we're going to subtract the log base a of v. Almost feel like Dora the Explorer right here. Yay, you did it! Dora, Dora, Dora the Explorer! Alright, I digress. This also works for the natural log, u divided by v. This is going to be equal to the natural log of u minus the natural log of v. And then our last property here is the power property. And it's kind of what you think of. Inside the logarithm, I have a power. I have another exponent. So if I have a log base a of u raised to an exponent n, that's the same as n times the log base a of u. And it works just like magic on the natural log as well. If I have log base or log of u raised to the n, natural log u raised to the n power, that's the same as n times the natural log of u. Okay, so that's pretty much all the information you needed to do all the problems from the worksheets that I've given you. So for now, let's look at an example problem. Okay, so for our example problem, let's say I have, let's see, what would be a good example problem? Okay, here we go. Let's say I have log base 3 of 6. Well, if they say simplify this, what I can do is I can rewrite this 6 as two numbers. That would be 3 times 2. And because I have multiplication in here, I can split it up into two different logs. So I have log base 3 of 3 plus log base 3 of 2. Now log base 3 of 3 is the same as 1, so I'm going to cross that out and put a 1. So now I have 1 plus log base 3 of 2. Now log base 3 of 2 isn't really helpful. So you can do this two ways. Since you have log base 3, you can rewrite this, and of 2, you can rewrite it using the change of bases formula, which we still have the 1 out front. So this log base 3 of 2 can either become any base you want, or you can just make it base 10. And when you write base 10, you don't have to put the 10. So you just say log base 10 of 2 divided by log base 10 of 3. And then what you would do from here is you would put log of 2 and log of 3 in your calculator. If you had a slide rule, which I doubt you do, because those are kind of extinct, you would use that as well. So you'd have 1 plus the log of 2, which is about, so I should approximate my answer here. So this should be approximately equal to 0.3 divided by log of 3, which is 0.4. So if we did 2 log divided by 3 of log, and then added 1 to that, that gives me about 1.63. So 0.3 divided by 0.4 is about 3/4, or 75% I should say, 0.75, plus 1 is 1.75. Now the reason my approximation that I ended up with is different than what you would do on the calculator is because I didn't round until I got my final answer. Now I rounded here, but in the calculator I left the values of the log of 2 and the log of 3 in the calculator so that when I finally divided it, it gave me a more accurate approximation. So the actual approximation for this should be this. Okay, so that's an example of simplifying a log. Another example real quick, if let's say I have to solve an equation that involves a log. So let's see if I can't find a good example for us real quick. Give me a moment. Okay, so if I have seven times the log of 3x equal to 15. That's our example. So, in this example, first thing you would want to do is isolate the log. Like normal, you would isolate a radical or isolate a square or whatever you can do to get it by itself. So the first thing we're going to do is divide by 7, both sides of the original equation. So what happens is we get log of 3x equal to 15 divided by 7. From here, we want to convert this log. Remember, if you can't do anything with the log, you can always rewrite it as the exponential form. So this log in exponent form is going to be, remember, our base is 10 here. It's a hidden base of 10. So that means I have base 10 to the 15 over 7 power equal to 3x. Now I just have to simplify. So what I would do is get x by itself by dividing 3 on both sides. So this gives me x equal to 10 raised to the 15 over 7 power, all divided by 3. And if you put this in your calculator, well, this is your exact answer. But if they ask for an approximation, the approximation would be 46.32. Is probably, I mean, you can approximate even further, but you'd be writing a lot of numbers. So this is probably good for now. So you would put this in your calculator and find that this is your answer. And I guess I'll do a little bit harder of an example just for the heck of it. And I think I have a little bit of time. So let's say if I have the natural log of x minus 3 plus the natural log of x minus 2 equal to the natural log of 2x plus 24. You'll notice that the first term, natural log of x minus 3, is only valid if x is bigger than 3. Remember, you can't have the natural log of 0. So if x is equal to 3, this gives you a negative or a 0 value. So the natural log of x minus 3 only works when x is greater than 3. Same thing works for the second term. X has to be bigger than 2. And the last term only works if x is greater than negative 12. So if we require that x be any real number greater than all 3 terms, then all 3 will be valid. So if all 3 terms are valid, then the equation is valid. So that's the first thing you have to look at, is what are your restrictions? What is your restrictions on your domain? So first we're going to simplify. After we figure out what the domain is in our head, we're going to simplify this. So that you're going to use the properties of logs to simplify this. So first, I'm going to look at this addition. What does addition mean I can do with the two things inside the natural logs? You're right, multiply. So this is the natural log of x minus 3 times x minus 2. Next, I'm going to let each side of the equation be the exponent for base e. So remember this one property of if I have e to the natural log of x, that's going to equal x. The natural log and e cancel each other out, so to speak. They're inverses of one another. So that's what I'm going to do. I'm going to take e and make that be the base for both sides. So now what happens is the e and the natural log will reduce because they're inverses. So I have x minus 3 times x minus 2 equal to 2x plus 24. Another way to look at step 3, which is where we're combining the two, is if I have natural log of A equal to natural log of B, then A must be equal to B. So from here and here, you can also notice that this portion should be equal to this portion because I have the natural log in front of both. And then we just get right back where we started. So it works out both ways, no matter which way you simplify it. So now that we've got a simpler equation, we can solve. So I'm going to distribute and expand out x minus 3 and x minus 2. So this gives me x squared minus 5x plus 6 equal to 2x plus 24. Then I'm going to subtract 2x plus 24 from both sides. So I get x squared minus 7x minus 18 equal to 0. And the reason I want to do this is because I can now factor. And when I factor, this gives me x times x, something equal to 0. And what two numbers multiply to give me negative 18 and add to negative 7? That's negative 9 and positive 2. So if the product of two factors equals 0, you know at least one of them have to equal 0. So that means x minus 9 equals 0, so x equals 9. And if x plus 2 equals 0, then x will equal negative 2. Now remember, our values from above, we defined our domain as x has to be bigger than 3, x has to be bigger than 2, and x has to be bigger than negative 12. So if I have a value that's smaller than one of those, then this doesn't work. And x equal to negative 2 is smaller than 2 and 3, so that's not a solution. So 9 is my only solution to this value. And you can check your answer by graphing the function just to see what it looks like. Okay, so that's some examples for you guys. Here are your multiple choice and free response questions. Have a good night.